Hello everyone, my name is Diego and I will present a paper called Linear Control Compensator for a Variable Transformer in Wide Voltage Power Converters. This is going to be the outline for today. I will first introduce a little bit the need we have and the theory behind the plant modeling. Then I will go deeper into the model itself. I will show afterwards a small signal validation of the assumptions made to design the control law. Then, of course, the control itself, and I will finish with results, conclusion, and lastly, a slide with future work. We choose the dual active bridge converter as there is not enough or non-publication that uses a variable transformer with this converter. And why a variable transformer, will be useful. If you see here, when we're using the converter at nominal power, we can have multiple conversion gains. So we can have, for example, a charging cycle of a battery. So we'll have lots of voltages here, but when we want to deliver less power, we see that we're going to start having switching losses in the converter. And how we can compensate this, for example, if the voltage is low, the power is low, we can increase the conversion gain. And how can we do that? Well, we propose a variable transformer. Of course, there are some ways to compensate the amount of power with phase control, but this is a little bit harder. So what we propose is we have a variable transformer, which is here, which is let's call it a normal transformer with a primary and a secondary side, but we saturate some parts of the transformer. And with this, the amount of magnetic flux inside changes, and we can have a different turns ratio. To model the plant, we use the gyrator capacitor theory, and basically it follows a differential equation. So when we add voltage or current into an inductor, depending on the amount of torque of the number of turns, a magnetomotive force is induced, and thus magnetic flux start flowing inside the core. And in the normal, let's say in the simpler reluctance model, we will have a reluctance model in the magnetic behavior, but here we will have a permeance model that follows the capacitor model, the capacitance model. So it would follow a differential equation. So it will be easier to design the control law. So for the structure of the transformer itself, we propose this this core, which I'm going to describe now. You see here that we have two cylinders, a blue one and a red one, which is the primary and the secondary side of the transformer. And we have this third leg, where the magnetic flux here in blue arrows is going to start passing normally. But if we see here, the top view, we will see that we add an auxiliary winding here that is going to generate a flux like this. This flux is going to get saturated, and thus we're going to have less flux crossing by this section. So we will saturate this leg, and then the equivalent number of turns is going to change. This is the representation that we have. So this is the flux that is sharing between the primary and the secondary side. We have two secondary sides, two secondary windings, and then this is the flux of the control leg. So what we are assuming here is that the interaction between the two fluxes are minimum and they are orthogonal. And if they are minimum and orthogonal, we can model this side of the plant separated from the transformer. So it's easier for us to design a small signal model. So following the differential equation, we can have, and following the permeance model in saturation. So with here, if we increase the magnetomotive force in the permeance that is represented by gamma, we will see that this value increases too much, so this will go to zero, meaning the permeance go to zero, meaning the reluctance go to infinite, meaning there is less flux crossing through the auxiliary leg. We propose also a change of variable for the differential equation, as we want to control permeance and not magnetomotive force. We make the corresponding change of variable, and we have this expression. So we did a finite elements small signal validation, and we can see here that the flux of the main core is spinning around here, and that the saturation is here. So of course, when it's more saturated than non-saturated, we have a reddish color, and we can see here a gap, meaning that the saturation flux is not going into the main flux, and the main flux is not going to here, of course, in a small signal. Uh, this is the small signal we designed in Simulink. So basically what we have here is that we have a step. So we change the amount of the voltage that we have in the secondary side. And with this, we want to compensate it with the variable transformer. So the change in the voltage by a small signal model that we already published. We calculate the reference for the permeance of the controller that we want to get. And then we calculate the trade-off that we also have, that when we change the equivalent number of turns, the magnetizing and the leakage inductance also changes. To decide the control, we use full state feedback control theory, as if we want to control then other parts of the transformer, other variables, or we add the large signal model, we can, with this theory, easily make an observer and make the controller more robust. This is how the permeance behaves with the formula that I already showed you. And if we want to control this region, which is saturated region, or this region, which is linear region, the best way is to linearize it here in the elbow, in the second elbow, because here we can control actually changes in the linear and the saturation mode. So we choose the second elbow to do the linearization. Also, we're going to have, of course, oscillation that is going to increase the error. But if you see here the behavior of the actual core that we're using, if we add small currents, here the mu changes, meaning the permeance has a lot of changes as well. So when we add small currents, the error is bigger than when we go to saturation. Here the equivalent inductance, the equivalent turns ratio, the mu doesn't change. So we're going to have less and less problems with the controller. We make this as we're going to have oscillation that we didn't take into account in the small signal model when we add the large signal model. Also, here is the results. When we saturate the core, we were able to change it theoretically, the equivalent number of turns from 2.5 to 1. And we can also see how the leakage and the magnetizing inductance changes. And if you remember the transfer function, or you know the transfer function, you will know that if we decrease the leakage inductance, we will have a change also in the power delivered. So this is a trade-off that we need to take into account for the implementation in the future work. So as a conclusion, we can change the equivalent number of turns by saturating parts of the core. The interactions that we have depend mainly on the core shape, and as we propose the structure in the air gap in the distribution in the core as well. That's why we add the losses in the model, and it also depends on how proper the plant is modeled. In saturation regions, we know that for big changes, we're not going to have much problems in the controller. So a proportional controller is enough to control the plant. And the trade-off that we have, of course, is the leakage inductance that I just mentioned. We did actually, additionally, finite element validation in large signal, and we see here that the gaps that we saw at the beginning, they are not actually not real gaps. We have interaction between the fluxes, and here we can see that the simulation shows that we couldn't change the equivalent number of turns to almost one, as I showed you before. But we can see here that the oscillations are quite small when we saturate the core. So that is useful for us because the idea of the controller is that it is able to keep the reference, and perturbations and oscillations doesn't affect it that much. But characterization of the core in saturation is going to be needed, as this comparison maybe is not that fair, as Maxwell, the software that we use, they use extrapolation for the curves after the point of saturation. And also we can not avoid that the structure really affects, and if we don't have a good structure, then we're going to, the small signal model is not going to be enough. We would like to thank also ECPE, which they partially funded our project. And thank you for your attention. I look forward to listen to your questions and or comments.